All right, so let's try 33 and 5.2 and see if we can get some built-in warm-up. Okay, so this has a whole giant thing. First things first, they want me to, so I'm kind of thinking AY double prime plus BY prime plus CY is 0, which is what kind of thing?
Second order differential equation.
Second order linear constant coefficient homogeneous differential equation. Cool. So I'm supposed to suppose that this thing is such that when I consider the associated characteristic equation, right? So like take this, turn it into R's. So I got AR squared plus BR plus C equals 0. And after solving that, I find that R is R1 or R1. Right, it's got a repeated real root. Is a root that's repeated necessarily real?
Does it? I'm gonna guess like.
Yeah.
Plus or minus.
Yeah, because the discriminant.
Yeah, sorry.
Yeah, because the discriminant's 0, so it's necessarily minus b over 2a. Right? So not only do you have a real root, you actually know what it is. It's the critical point of this function, right? The vertex. Okay, and I'm supposed to think of e to the rx as a function of two real variables, x and r. Okay, A. Y of, say, r and x is e to the rx. And now I'm supposed to do some calculation here. So there's a, the number A, not the part A. A, and then take the second partial with respect to x of e to the rx and add that to b times the first partial with respect to x of e to the rx. Basically just do this calculation, right? Okay, thoughtsies?
Oh, is there no C part on that? There's a C, right?
Oh, there is a c.
And there's a.
Plus c
Non-zero.
e to the rx. And then there's equals some stuff that I'm supposed to figure out, right? Okay, so if you look at this, what's the second partial with respect to x of e to the rx?
R squared to the RX.
Okay, so I got a r squared e to the rx plus b, and then what's the first partial of e to the rx?
R e to the RX.
R e to the rx. And then plus c e to the rx, right? You guys with me on that? Okay, and they note that I'm supposed to, okay, so this is e to the rx times ar squared plus br plus c. Right? Yeah. Okay.
And you know it's repeated.
Okay, and then I know that there's a repeated solution, right? You guys with me on that? Which means that if I consider the AR squared plus BR plus C equals 0, I get R1 and also R1 again, right? Okay, but they're telling me this is supposed to be like R minus R1 quantity squared. Seems a little weird, right? So let me think about what R1 was. What did I say? I knew R1 was
Negative B over 2A.
negative B over 2A, right? You guys with me on that? Okay, so that would mean that negative B is 2A R1, right? So B is 2A R1? Negative? Yeah.
That's just saying that the stuff inside the square root and the quadratic 0, right?
Yeah.
Okay.
Yeah, if there's a repeated root, there's a discriminant, right? This crap all inside the square root. That's 0. So if I make this substitution, right? Take b, which you know in terms of a and r1, and shove it in here. You get e to the rx times ar squared, oops, minus 2ar1 plus c.
So it's not R1R.
It is r1r, as you say.
But then R1 is equal to R, based on the given information.
I don't have this equals 0, right? If I knew that this was equal to 0, then I'd know that r1 is r. But I don't know this is 0. So I think I need to get the c out of here too. So what was this thing you guys said about the thing under the square root, 0?
The square root of
Is b squared minus 4ac.
Oh, b squared minus 4ac is 0, right?
Okay.
Right, which tells you maybe
C equals b squared over 4a.
c is fiddle just about b squared over 4a, right? But you know what b is. B is minus 2ar1. So you know that c is minus 2ar1 over 4a, oops, and squaring the top, which will give you 4a squared r1 squared over 4a.
Which would be R1's, I'm sorry, A R1 squared.
Yep, so you get a r1 squared. So we can replace c. A r1 squared. And now you might factor an a out of all that jazz.
So it's just 1 minus R1.
And then that's r minus r1 quantity squared. Okay, so that. So I got a e to the rx times r minus r1 squared. Cool. That's all they asked me to do in the first bit, right? Like take the first bit, show that when you differentiate, or when you take this equation, you get that one. Okay, I did that. Sure. It was weird. I don't know why I did that, but I did. Okay, then part B, differentiate the result from previous to obtain something. So I'm supposed to take my equation from the first part. So my equation from the first part, oops, I dumped some of it. So my equation from the first part says I have a times the second x partial of e to the rx plus b times the first partial of e to the rx plus c times the not partial of e to the rx was e to the rx, oops, a e to the rx times r minus r1 all squared, right? And then they want me to do what to this thing? Not excited. So they said differentiate with respect to r. So take this and do a partial with respect to r to the whole thing. You guys cool with that? So
Okay.
yeah, it looks nasty, but like we can probably do it. Okay, so I should get a times the partial with respect to r. Because I know the constant can come through, right? But then I've got this partial with respect to x, right? I've got this second partial with respect to x. Can I interchange the order of the partials?
Is there some sort of chain rule there?
Yeah, there's some sort of theorem
I
there.
don't think you can with partials, right? Because that would be like f x x r, right? Which is not.
Which is not necessarily FRXX, yeah. That's a reasonable complaint. right? This would be, interchanging these would be assuming that Claro's is true about this particular function, right? Do I feel like I have a good chance of Claro's being true for e to the Rx? Yeah, I feel like I've got a pretty good chance of that happening. But let me just not assume. They didn't assume, right? So they're just asking you to demonstrate. So I got b partial with respect to r, partial with respect to x, e to the Rx, plus, how about that last guy? Can you hit that one?
Yeah.
Yeah, I think that one you can hit, right? It doesn't have a partial. You don't have to worry about which
oh,
partial
sorry.
you're doing.
Over
Just freaking
differentiate.
do it.
I just copied them.
So if you're hitting this with a partial with respect to r, what do you get?
X, CX e to the Rx.
C
R.
x e to the Rx. One and an r.
Wait, we're differentiating with respect to R, right? Not X.
Yep. I'm differentiating with respect to r. So I got
Oh, no, yeah.
I got the constant,
Yeah, x.
and then I got e to the
Yeah.
stuff, and then I got the derivative with respect to r of the stuff.
Yeah.
And then I got, on the other side, I got a, what do you need over there? Product rule,
Yeah.
right? So to
So-
get the product rule of this stuff, I need a times the first thing, times, or sorry, a times the derivative of the first thing, times the second. I'm just trying to be clear and write my derivatives towards the end. Plus, what should the other one be?
The R partial, R minus R1 squared.
Yeah, so partial with respect to r, r minus r1 squared, and then
E, just E to the Rx.
and then just an e to the r. You guys good with that? Okay, so the left-hand side already matches what they told me to get, so I'm going to leave that alone. The right-hand side, what's the partial with respect to r of e to the Rx?
X,
Okay, yeah.
E to the Rx.
X, E to the R.
So I got my x, and then there's a e to the Rx. And then over here, I got a plus a e to the Rx. What's the derivative of that weird thing?
Two
Quantity,
quantity,
R minus R1.
Twice the thing to the one lower power is
To
1 times the
derivative of the inside, which is just 1.
derivative of the inside is also 1. So I really have a 1. But- Cool. All right, how close am I to what they told me to get? Close-ish. Up to algebra. So they want me to group some of this stuff. So what do you see in here that I can get out of this right now?
A to the Rx.
Yeah, I think there's an A, there's an E to the Rx. What else you got in common there?
R minus R1.
There's an R minus R1. And then what are you left with?
R to the Rx minus R1 to the Rx.
We got an X, R minus R1 plus
2.
2. That seems weird, right? Which is up to rearrangement of order, exactly what they told me to get. Yeah, they wrote it in kind of a bizarre way. They wrote it in what a lot of people would kind of consider mathematically standard notation. They put this thing in the front with the numbers first and then the variables after, and then they rearranged this thing so that variables were in kind of more
Yeah, for some reason they
like
put the
closer
R-
to
They
alphabetical
put the R
order.
and the R1 minus in between the E and the R.
Yeah, so what they did was they literally just rearranged for alphabetization. There's a whole very silly set of rules for the order in which you write things. And they should go numbers first, hence my 2. And then that whole thing has to go next. So I got a plus, and then they probably write the R minus R1 first, because that comes alphabetically
Yeah,
before
and then
X. And then there's an A, And then what's the next thing alphabetically out of that crap?
R minus R1.
Well, actually it's E, but E's a number, so E.
Yeah, so they go with the
Yeah.
letter.
So you do variables in alphabetical order, and then at E to the RX. So that's a super silly set of rules, and I don't care whether you know them at all.
Why is the A sandwiched in there?
Because it's first alphabetically after the thing with the numbers.
Because it's a super silly set of rules.
I
don't
think
know.
that looks
It's a
worse than
silly
the
ass set of
AE to
rules.
the RX, I think.
Yeah,
I think it gets worse. When you
yeah.
do that.
There's a set of rules. I don't care what they are. Don't worry about it. They get even weirder when there's Greek letters mixed in. And they get super duper weird when you start mixing Hebrew. All right, so let's
Can we throw a win in there too?
Oh yeah, we should throw a win in there. That'd be great. All right, so then next step, we're supposed to reverse the order of partial derivatives in the first two terms on the left-hand side to obtain something.
So,
In other words, apply Claros. Right? So right now what I'm sitting with is I have this equation that I got from just considering this weird object. And so I started with some funny object. I calculated what that was equal to. I differentiated both sides with respect to r. And now I'm going to apply Claros to the result. So take this whole thing and hit with Claros. So the right-hand side is not going to change. And so my right-hand side here will continue to be this bizarrely arranged little equation. So I've got a 2 plus r minus r1 times x times a r minus r1 e to the rx, whatever. And then over here, I should rearrange the order of the first two terms. So they're saying, take that a and make it, instead of partial with respect to r, then twice partial with respect to x. I should do the partial with respect to x's. So do two x partials, and then do a r partial of e to the rx, and add to that the partial with respect to x, and then the partial with respect to y of e to the rx, plus cx e to the rx. Like, just basically go back and consider what would you get if you did the derivatives the other way around. Should be the same thing, because e to the rx is nice and continuous in basically all manners. Right, so Claros should apply. So if I actually do this, what's the partial with respect to r of e to the rx? Perfect. So I need to take two x partials of x e to the rx, and I need to add b and take one x partial of same thing, x e to the rx, and add that to cx e to the rx. Right? And I know what I should get. Right? Like, I have to get that jump. So I have to get 2 plus r minus r1x a times r minus r1 e to the rx. Right? Like, I know I have to get that stuff because Claros is true. You whining about my r?
No?
No.
Actually,
You have two R1s.
R1 minus
Left.
R1.
Oh, see, if you do r1 minus r1, it gets a lot easier.
Also, since we can see
Special
the,
trait. Yeah, special
see that
trait.
question above, why don't you just draw an arrow?
You just hit that with a subscript 1.
All right. Because I wanted to spend a bunch of time writing and saying that. Okay, at any rate, now I need to calculate these two partials, right? Okay, so let me do that somewhere not here. Let me do that over here. Partial with respect to x of x e to the rx. you should need a
Product.
product rule, right? So you do derivative of the first thing is
Uh,
1 times the second, so you got e to the rx
You could
plus
go to any side.
X squared.
X.
X.
You sure it's an x squared?
Oh, no. R, X.
Remember, you're differentiating with respect to x
Yeah,
now.
it's tripping me out.
So you need the first thing, x,
R.
times the e to the rx times the derivative of rx, which is r.
Yeah.
Right, and this guy here is the partial with respect to r of x times, or r times x. Partial with respect to x, how about I differentiate with the right variable? So you get this, and then I need to hit it again, so I need the partial with respect to x of that stuff, and I should get
R e to the rx.
r e to the rx
That's the same thing you just did.
plus r times the same crap I just had. Okay, so I drop it all here. We got now a times r e to the rx plus r e to the rx. Oh, nice. There's two of those, and then there's a r squared x e to the rx. Did I jack that up yet? No? I should probably, that was dumb to say. And then I have b times the first thing, which was a e to the rx plus
X, e to the rx.
x r e to the rx. And then I have a plus cx e to the rx. And I know that's supposed to be this other thing. Okay. Now what the hell, I'll write this other thing down for 1 second. Okay. Why was it interesting to write that down?
Because there's no B's or C's in it, right?
Yeah, because we subbed in the other stuff.
Yeah, so someplace here I should be able to get rid of like B and C,
Do we need to use those old?
right?
Yeah.
Maybe I can just notice something. Like, let me see. Over here, there's going to be some x e to the rx's, right? And some regular e to the rx's. You guys see that? Over here, there's going to be some regular e to the rx's and some x e to the rx's. You guys see that? So right now I'm just playing along here. They told me I should reverse the orders, get this, set R1 and B and D. So B was the thing here, and D was actually just this. So I went one step further than they told me to, because I'm dumb. Okay, so let me call this equation here is B. This equation here is D. They told me set R equals R1 in both of those. So if I take B and evaluate at R is R1, right? So if you take this guy and shove R equals R1 in there,
The whole thing is 0.
you get 0 on this side.
Cool.
Good. On this side, you get A times the partial with respect to x squared of e to the r1 x plus b partial with respect to x of e to the r1x plus c e to the r1x, right, equals 0. Okay, what's that saying? This whole thing?
The R1 solves it, maybe?
Yeah, that one's saying e to the r1x solves the differential equation you were given before, right? Because I made it that way, right? Okay, now if I go to D and plug in R1,
The right side is still 0.
I get D evaluated at R is R1, and I'm going to get the right-hand side is going to be 0, right? And I'm going to get A partial with respect to x squared of x e to the r1x plus b partial with respect to x of x e to the r1x plus c x e to the r1x is 0. And what does that mean?
X.
Oh, that's the other solution.
Yeah, that means x e to the r1x solves. So this is twofold, right? The result you're getting here is twofold. I don't have the colored marker here. Okay. So the result you're getting is this first b evaluated at r equals r1. That tells you e to the r1x is a solution. The second d evaluated at r equals r1 says x e to the r1x is also a solution. Right, and then you could calculate the Wronskian to demonstrate that those are linearly independent. Or you could just look at the functions and tell that they're linearly independent.
Is this the proof of Tuesday lecture?
Yeah, this is kind of another way to see that thing we talked about on Tuesday. Right, like instead of going through the whole Wronskian rigmarole and setting it equal to e to the minus p of x and like cranking on it, finding the solution, this is just like, oh yeah, you could just do it this other way and notice the same thing.
So what did we do though, really?
Yeah, what did we actually do? So what we actually ended up doing was thinking about e to the rx as a function of two variables. And then we differentiated with respect to x first to see the solution we knew about. And then we thought, well, what if I differentiate that equation with respect to r? The reason you might do that is that when a root's repeated, right? When it's a repeated 0 of a function, of a polynomial function, that means the derivative's also 0 there. That's a little bit weird. But if you think about it, you'll kind of see that it's true. So if you had a function polynomial of x, right?
Oh,
Like x minus 1 squared.
Yeah, so if you had a polynomial that looked like x minus z1 times x minus z2 times x minus z3 squared, right? If you differentiate this thing, you get a whole bunch of product rule crap, right? But in each of the terms, there will be at least one x minus z3. That's kind of because this thing is doing a touch and turn. You guys know what I mean by that? Like the graph. Where it goes through z1 over here, it goes through z2 maybe there, and it goes through z3 here, right? But the function's not actually changing sign through z3, right? So it might be doing something like this.
so what did you say, that there'd be a z3 in all of what?
There will be an x minus z3 in the derivative. in all the terms. So if you calculate p prime of x, you get a bunch of stuff, right? You'll get like something, maybe plus another thing. Like who knows how many terms you get. We could never figure that out. I'm just kidding, it'll take a couple of seconds, but I'm too lazy to do it. But each of those things would have as x minus z3 in it.
So we just factor in x minus z3 out.
So we factor in x minus z3 out, and then just notice that the zero product rule says that when the derivative is 0, right, that would mean that part has to be 0, so it's a solution. Or we could notice that if I plug in z3, I get 0 out. Right. So if you have, and this is just with degree 2 that this touch and turn thing is true. But if you have degree 3, it still has a flat spot there, and it acts locally like a cubic. So you'll still get a 0 of the derivative. So they just observed something clever about zeros. Right, they knew for whatever reason that when you differentiate, if you have a repeated root, it doesn't go away. So they just did that, and then they said, okay, well, what do I get? Well, what I get is x e to the rx instead of e to the rx being your solution. Is that going to make sense? That's sort of magical.